Have you ever wondered what would happen if two colossal black holes suddenly merged near our solar system? What cosmic fireworks would unfold, and how would this cataclysmic collision ripple through space and time? Imagine titanic gravitational forces, space-time rippling like a cosmic fabric, and intense energy unleashed in a silent ballet of destruction and creation just a few light hours away from our planetary home. This is not just an astronomical curiosity. It's a frontier of modern physics that tests the limits of our understanding of the universe. If such a merger happened close to our solar system within a few light years, these gravitational waves would pass through us, stretching and squeezing space-time itself. While humans wouldn't physically feel these effects because the distortions are incredibly minuscule. Sensitive instruments like LIGO and Virgo would detect the gravitational waves produced by a black hole merger through a sophisticated method called laser interferometry. Each observatory consists of long L-shaped tunnels where laser beams travel down both arms and reflect off mirrors suspended with extreme precision. In normal conditions, the laser beams recombine perfectly, canceling out any light at the detector. However, when a gravitational wave passes through, it distorts space-time, causing tiny changes in the lengths of the tunnels, much smaller than an atomic nucleus, making the laser beams arrive out of sync. This disturbance creates a measurable signal that reveals the passing gravitational wave. The two LIGO detectors in the United States work together with the Virgo detector in Italy, using the differences in arrival times and signal strengths to precisely locate the cosmic source and confirm the wave's properties. This network dramatically reduces false positives and allows for detailed study of these extraordinary events. However, the gravitational pull of nearby black holes could have more substantial effects. If the merged black hole approached or disrupted the orbits of planets, it could destabilize the solar system drastically, changing planetary trajectories or even ejecting planets from their orbits. But this scenario requires the black hole to come extremely close, much closer than a few light years. The newly merged black hole is a more massive singularity, sometimes spinning rapidly. Surrounding gas and dust can heat up intensely as it accelerates into the black hole, producing luminous X-rays and gamma rays. This could lead to bursts of high-energy radiation affecting cosmic rays and potentially impacting Earth's upper atmosphere. However, the severity depends on distance. A merger within several astronomical units would be catastrophic, but mergers tens or hundreds of light years away mostly pose observation opportunities rather than danger. The cosmic environment becomes energized, influencing solar wind patterns and magnetosphere dynamics subtly but detectably. Gravitational wave observatories like LIGO and Virgo have directly detected hundreds of black hole mergers by measuring ripples in spacetime at extraordinary sensitivity. These discoveries have allowed astrophysicists to confirm key predictions of general relativity under extreme conditions, including Stephen Hawking's area theorem. This theorem states that the total surface area of black holes cannot decrease during a merger. Recent detections have provided the clearest evidence yet, showing the final black hole's area always exceeds the combined area of its precursors. Ongoing and future observations push our understanding even further. LIGO, Virgo, and Kagra together have documented the most massive black hole mergers ever detected, some resulting in single black holes over 225 times the mass of the Sun. These events challenge current models of how black holes form and evolve, showing the existence of so-called second-generation black holes, objects produced not from stellar collapse, but from previous black hole mergers. Some of these mergers involve black holes with masses and spins that defy existing theories, indicating they likely originated in dense, chaotic cosmic environments where repeated collisions are possible. ESA's upcoming LISA mission will expand this capacity into space, detecting black hole mergers at even greater distances and with higher accuracy. Each detection not only reveals details about the population and environment of black holes, but also accelerates advancements in allied fields, such as quantum sensing technology, big data analysis, and deep space observation. As gravitational wave astronomy matures, these discoveries fundamentally reshape. While extremely unlikely, a black hole merger near our solar system vividly illustrates the extraordinary forces shaping our universe. These cosmic collisions underscore the fragile balance that sustains our planetary system's stability amid vast gravitational powers. By studying these events, humanity gains profound insights into the fundamental workings of space, time, and gravity, enhancing our grasp of physics under extreme conditions. It also reminds us of our humble yet precious place within this cosmic dance, where immense and violent phenomena coexist with the delicate environments that make life possible. For context, the closest known black hole, Gaia BH1, is approximately 1,560 light-years away, about 370,000 times the distance from Earth to the Sun, emphasizing the vast, safe separations that protect us from such extraordinary events. Yet, the study of these immense collisions and their subtle ripples deepens our curiosity and drives exploration toward understanding the universe's most dramatic processes. If you enjoy journeys into the hidden side of our universe, subscribe to The Enigmatic. More untold stories are on the way.